So in the data frame that we generated above, we've basically seen that there is no way in which we can recover any relevant treatment effect. So we're going to change the question a bit and we're going to ask, are there conditions under which we can find our treatment effect? And the treatment effect we're looking for is that tau is equal to 3, which is the effect of training on the compliers. And there are 3 cases in which indeed we can identify tau equal to 3. The first 2 are pretty trivial, the last one is a bit deeper. So in the first situation, we're going to generate a new data frame using our function data simulation that we defined above. And the only thing we're going to change is the fraction of the different types that we have. So in this case we assume there are compliers only, so the n, the fraction of compliers, is going to be equal to 1, and there are going to be no always takers and there are going to be no never takers. Yeah, so we can generate our new data frame, and we call it the data frame of compliers only. And then we can do the same calculation that we did above. So we take the average earnings of everybody with training, and we subtract the average earnings of everybody without training. And when we do this, indeed we get our number tau equal to 3. Yeah, so this number is close enough to 3. That indeed gives us the treatment effect that we were looking for. So one case in which we can find it is basically when there's only one group, there are only compliers. These compliers follow the regulation in the sense that they only get training if they get invited, and they don't get training if they don't get invited. And training is distributed randomly. Yeah, so it does not, for instance, depend on the resulting effect of training on earnings, but it's randomly distributed. And then indeed, under these conditions, we can find our treatment effect. The second case in which we can find the treatment effect is when we generate again our data frame, but now we do not change the fraction of the different groups, but we change the expected earnings for each group conditional on no training and the training effect, the tau. And if we assume that these 2 are the same for all the 3 groups, so for the complier, the always taker and the never taker group, so we have symmetry here, so it's 1 for all 3 groups without training, and the training effect itself is 3 for all 3 groups. So we generate our data frame, df, for the homogeneous case, and then again I can compare the conditional mean, conditional on being trained, and I subtract the mean conditional on being not trained. And if we calculate that again, we're getting pretty close to 3. Yeah, but again, this case is also fairly trivial, because again there are no heterogeneous treatment effects anymore, that's because I've assumed symmetry in this case. So the case which is a bit more complicated, but where we can still identify our effect, is the case where we look at one-sided non-compliance. Yeah, so again we generate our data frame, and the only assumption that we make now is that there are no always takers. Yeah, so the only non-compliance that we have are the people who do not go to the training, although they were invited for it. Yeah, so now we have 50% of our individuals are compliers, and the other 50% are never takers. Yeah, and apart from that, everything is the same. And then there is this claim by Angrist and Pischke. Oops, didn't mean to do that. So let me restore this equation. We don't need this A here either. So they claim that in this situation, where there are only compliers and never takers, so I have 2 different groups, so I have heterogeneous effects, I can still identify my treatment effect, so with tau equal to 3 for the compliers. If I take the difference between expected earnings, conditional on being invited, so ZE is my instrument here, and it's whether or not you're invited, minus the expected earnings for the groups that were not invited, for the group that was not invited, so ZE is equal to 0. And then I divide the difference between those two expectations by the conditional probability of being trained, conditional on being invited. Yeah, so basically we're going to calculate this thing using Python, and we're going to see whether it's equal to 3. Yeah, we're going to do that in 2 steps. So the first thing is to actually calculate this correction term here in the denominator. So in order to do that, we need a bit of base rule. So basically what we want is di equal to 1, conditional on ZE being equal to 1. Yeah, so using base rule, that basically means that what I'm interested in is the probability that you are trained. So di is equal to 1. Oh, it's equal to 1. And you were invited. So this is equal to 1. Divided by the probability that you were invited. Yeah, so this is the correction term that I need to calculate. So there's a conditional probability, so it's a probability that you were trained, conditional on being invited. And you can calculate that conditional probability with base rule in this way. Again, I have the same problem here. Okay, let me go here. Okay, so here we are. So now we're going to do this in Python. So I have my correction term. So I need to calculate using Python this conditional probability. So it's going to be numpy sum. So first we do the numerator. So we get data frame one-sided. And we're going to have data frame one-sided invited is equal to 1. And from that, I want to count the number of individuals that actually got trained. Yeah, so I'm selecting the group that was invited, and I'm summing over from this group the number of people that were actually trained. Yeah, so that's going to be, sorry about that. Trained is going to be a 0, 1 variable. So if I sum over them, I simply get the number of people that were trained. So that's the first part. And then I need to divide this by the number of people that got invited. So how do we do that? So again, I can do here numpy sum. I could also use the length of that vector, but I use the sum here. df one-sided and then conditional on df one-sided dot invited is equal to 1. And from this I'm going to count the number of people that were invited. So let me see, this seems to all add up so that I don't get any errors. So this is my correction term. So basically that calculates this thing over here. So first we have the people that were invited and trained, because I'm summing over the people that are trained. And then I divide it by the people that were invited, so I condition on that, and I calculate the ones in invited, and of course there are only ones here because I'm conditioning on invited equal to 1. So now let's see whether we can actually calculate the equation given by Angrist and Pischke. So I'm going to have the difference between these expectations divided by the correction term that I just defined. So what is this difference? So I'm going to take the NumPy mean of df one-sided, where df one-sided dot invited is equal to 1. So let me see, I need to close this bracket and then I need to close that bracket, and I subtract for that np mean, so df one-sided, and I condition on df one-sided dot invited is now equal to 0. And again, I'm interested in the earnings, so that's what I take the average over. I take the mean over that, and then I evaluate this expression. And I made a mistake somewhere because this is not what I was expecting to see. So I take the mean over, yeah, okay. So I forgot my earnings here. So I take NP earnings, so let's do this again. Yes, and then we find 3.02. So this is close enough to the effect that we know for the compliers, that tau is equal to 3. Yeah, so in this situation where I have heterogeneous treatment effects, yeah, I have two groups. I have compliers and never takers. They feature different effects from training, but with the equation provided here by Angrist and Pischke, I can still identify the treatment effect that I put in my own data set, in the data that we generated ourselves. Yeah, so this is a slightly more complicated situation than the two others we looked at before, because I still have this heterogeneity, but if there's one-sided non-compliance, so there are no always takers, there are only compliers and never takers, I'm still able, using this equation, to identify the treatment effect that I put in the data when we generated it.